Okay, once again, welcome to Nisiki Academia. In this video, we are going to be looking at Math 114.2, which is set logic and numbers, okay, also known as algebra, linear algebra, okay. So basically, we'll be starting with sets, okay. We'll try as much as possible to touch the key areas of this course and demystify it to ensure that it gets a clearer understanding. Okay, so what are sets? Okay, a set is a well-defined collection of distinct objects called elements or members. A well-defined collection of distinct objects. Distinct is a keyword. Okay, distinct objects that are called elements or members. Elements or members. All right, so the objects are distinct and these objects are called elements or members. All right, so sets are usually denoted by capital letters A, B, C. This is how we represent sets. We use capital letters to represent sets. Okay, so basically, for example, we can have a set of five natural numbers. Natural numbers are counting numbers: 1, 2, 3, 4, 5, 6, 7. So we can have the set of five natural numbers. You can see set A has 1, 2, 5, 7, 9. These are five natural numbers because they are five counting numbers. So this is a set of distinct. Okay, this is a set of numbers that are of the same group. The fact that we are putting them in a set, it means that there is a distinct, or there's a clear relationship between every member or element in this set. All right, we can say a set of vowels in English. Okay, we can say a set of five vowels in English. You can say A, E, I, O, U. Okay, this is just a set of vowels. Of course there are five, but a set of vowels in English. All right, so basically, when we talk about sets, we have types of sets. All right, so the types of sets we have, well, the first type is called the finite set. Okay, it can be in any particular order, but we have finite set. Finite set has a fixed number of elements. All right, the elements in a finite set are actually fixed. Okay, are actually terminating. It's not continuous. All right, it's not continuous. For instance, if we have a set of four numbers, all right, this is a finite set: 1, 2, 3, 4. Okay, it's not tending to infinity. Okay, it's not tending to infinity. It's a finite set. All right, so number two is what we call infinite set. Okay, it's like the opposite of finite set. All right, infinite set. All right, it tends to infinity. Okay, for instance, now we can have 1, 2, 3 dot dot dot, then infinity. This is a set of positive numbers, positive integers. All right, you know that positive integers, in fact, numbers cannot have a terminal point. All right, there's no point where you get to and you say the biggest number in the world. No, there's no such thing. All right, okay, so that's it basically. Then we also have what we call a universal set. All right, we have what we call universal sets. Okay, so universal set is a set of all possible elements, which are being discussed or evaluated. All right, which are being discussed or evaluated is denoted as U. Okay, denoted as U. All right, now we also have what we call subsets. Okay, so subset is every element. If, for instance, now if you have two sets, okay, you have two sets, set A and set B. So every element that are in set A are also in set B. All the elements in set A. For instance, now if we have set A to be 1, 2, 4, and set B is 1, 2, 3, 4, 5, 6. You look at it very well, you realize that the elements in set A, which are 1, 2, and 4, are in set B. Okay, they are in set B. So elements that are in one set that are all in another set means that this A, all right, this set A is a subset of set B. Okay, so this is how we denote it: subset of B. All right, then we also have what we call power set. But before we look at power set, okay, there is what we call set cardinality. Okay, set cardinality is denoted as, look at how it's spelled, cardinality of sets. denoted as n. So cardinality of a set is of course the number of elements in that set. For instance, now look at set B. Set B has 6 elements, so n is equals to 6. So if you want to look at the power set now, power set now is 2 raised to power n. Okay, so if we want to look at this set B now, we say 2 raised to power 6, which will be 2 times 2 times 2 times 2 times 2 times 2. Whatever value that you get is your answer. So you have to know the number of elements in a set first. Then after that, you can check the power. If you don't know n, you cannot get p, which is the power set. All right, you cannot get p, which is the power set. So it's very important to note that. Okay. Then we have what we call set operations. Set operations. Set operations. So when we say set operations, we have different types of set operations. All right, we have different types of set operations. We have the union. We have one we call union. Union for two sets, for instance, we have set A and B. Union of set A and B is A union B, like this is how it's denoted. So what does it mean by A union B? A union B is a combination of the elements in A and B. Union, bringing the elements of A and B together without repetitions. For instance, now if we are still using okay, now let's use another set. Let's say set A has 2 5 6 and set B is 1 4 7 10. Okay, 1 4 7, let's say 1 4 6 7 10. I'm trying to repeat. So if you look at now, we have 6 6 here, but we will not come here and say A union B will not be equal to 1, it will not be equal to 2 5 6 1 4 6 comma 7 10. That's not what we mean. We mean that you combine the elements in the two sets, combine the elements in the two sets without repeating. So A union B now should be, and most times it's best to start by from the increasing order from smallest to biggest. So you can say 1 2 4 5 6 7 and 10. All right, so this union, this is the union of set A and set B. Set A and set B. Okay, so we also have another set operation we call intersection. All right, intersection. So the intersect of A and B is denoted as this: A intersect B. Intersection has to do with elements that are common to both sets. If you look at these two sets now, we can say the A intersect B is equal to 6. How? If you look at the two sets, you realize that 6 is here, 6 is here. If we had 2 here as well, okay, if we had 2 here as well, then we would have said 2 and 6. So what is common to the two sets is what we call intersection. Now, mind you, okay, mind you, when we are looking at the types of sets, all right, when we are looking at types of sets, okay, it's very important also to state that we have what we call singleton sets. Singleton set is actually a set that has only one element. All right, we are going back to types of set, although we'll return to set operations. All right, but for instance, now if we have set A and just 6 is in set A, this is a singleton set because it has only one element. We have what we call null or empty set. A null or empty set is a set that contains no element. An empty set is either denoted as this or just simply an empty set. This is called phi. Look how it's drawn. It's called phi. All right, it's called phi. It's a sign that indicates emptiness of a set. All right, it's a sign that indicates emptiness of a set. All right, so now that is that. Now let's return to the set operations. All right, let's return to set operations. Now we have what we call difference. All right, we have what we call difference. We have what we call difference. So when we say difference of two sets, okay, what that means is that we're actually interested in, okay, we're actually interested in the elements in one set that are not in the other set. For instance, now if we want to look at difference of A and B, we'll say A minus B. And if set A, for instance, is equal to, let's say, 2 5 and 6, and set B is equal to 137. Okay, 137. Then we also have 8. Okay, let's just say 1, 2, 3, 7, and 8. Now a minus b now will be the elements are in set A but they are not in B. Okay, elements are in set A but are not in B. So now if you look at set A, what are the elements in set A? 2, 5, 6. Okay, which are the ones that are not in B? 5 and 6. So A minus B is 5 and 6 because 2 is in set B. So you cannot say 2 is not in set B. So the elements that are in set A are not in set B is what shows the difference. It's what shows the difference. All right. Then still on that, we have what we call complements. What we call complements. When we say complement, we are talking about elements in the universal set but not in A, or elements in universal set but not in B, or whatever symbol that you're trying to use to represent the set. So for instance now, A complement, for instance now, A complement is noted like this. This is how you write complement, or you say something like this. Okay, but most times it's represented this way. Okay, A complement most times represented this way. So if we have universal sets to be, let's say 1, 2, 3, 4, 5, 6, 7, 8. Okay, and set A is, let's say, 2, 4, 6, 8. I want to look for A complement. What are the elements that are in set in this universal set, but you will not find them in A? In the universal set, but you will not find them in A. Those elements are: 1 is not in A. Okay, 3 is not also in A. 5 is not also in A. 7 is not in A. Okay, so if you look at it very well, realize that these numbers are not in set A. So that makes these values the complement of set A. All right, that makes these values the complement of set A. All right, so now let's look at a question. Okay, let's look at the question, a past question. Now the question says, okay, so the question says if x is x such that x is a factor of 32 and y such that y is a factor of 48, then find x intersect y. All right, this is a very simple exercise. First of all, we need to know the factors of 32 so we can actually have the exact values that are supposed to be in this set. So it means that x, now factors of 32 are of course numbers that are divisible by 32 without that you will not have a remainder. All right, so those values are 1, 2, 4, 8, 16, and 32. Then factors of y are 1, 2. Okay, factors of 38, let me just say factors of 38 and 32 rather, and 48. Okay, so we have this for 38, this one now will be for 48. So y now will be 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. All right, so these are the factors of y. So now look at, we have been able to get the two sets. Okay, we've been able to get the two sets. So now it means that the intersection of these two sets, which is x intersect y, will now be the values that are common between x and y. What are the values we find in x and you also find in y? All right, so those values are 1, you see 1, you see 2, you see 4, you see 8, and you also see 16. So it means that this is your answer. This x intersect y. All right, so let's look at another question. So this next question says if set x is x such that x, this small letter x, of course you need to know that it represents the elements in the set. Okay, x such that x is a prime factor of 169. Okay, 169, and y, okay, is y is such that, okay, y is a solution to x squared plus 9x plus 14 equals to 0. Close. Now the question is find x union y. All right, now so you need to know prime factors of 169. Okay, the prime factors of 169. Now one thing you need to get is this, that if you want to get the prime factor of 169, basically the prime factor of 169 is 13, because 13 times 13 is what will give you 169. It means that your set x now is is 13. Now we have a quadratic equation here, so you now solve the quadratic equation. Now the quadratic equation is x squared plus 9x plus then plus 14 equal to 0. So now if you look at this, now you want to solve this quadratic equation. Of course, you look for two values that when you add will give you 9, and when you multiply will give you 14, and those two values are 7 and 2, plus 7 and plus 2. So it means that to factorize, now you get x plus 7 and x plus 2 now equal to 0. It means that you have x plus 7 equal to 0, x will be equals to minus 7, x plus 2 equal to 0, x will be equal to minus 2. All right, minus, so we have minus 7 and minus 2. So it means that your y now will be equal to minus 7 comma minus 2. That's what your y will be. By so there is a solution of this. So it means that you have to solve this. That's what we mean by solution of the, you have to solve this equation, and solving it now you're having minus 7 and minus 2. All right, so it means that now x union y now will be combination of set x and set y. So it means that you have minus 7, minus 2 and 13. All right, so this is the union of x and y. All right. All right, so we have another potential exam question before us. Say now we are going to be looking at elements of intersection with inequalities. All right, so this is a very core part of sets that of course people tend to ignore, but you cannot eradicate it from the knowledge of sets. Okay, now in the 2017-2018 exams of University of Port Harcourt, question 11 say let A be equals to x such that minus 4 is less than x and less than and equal to 6. B, x such that minus 1 is less than x and less than 1. C, x such that 0 is less than and equals to x less than and equal to 7. Find A intersect C. Now look at this. These are inequalities, guys. These are inequalities. All right, now we have to bring out the values, actual values for set A, set B and set C. Now they say x such that minus 4 is less than x less than or equal to 6. What this means is that now the values of x, okay, the values of x, minus 4 should be less than it, and this also x now should be less than or equals to 6. It's a number line. It's more like a continuity of values on the number line. So if we have the number line like this, and we have the number line, let's say now it is 0, we have 0 here. For instance, this will be minus 1, minus 2, minus 3, minus 4. Then this will be 1, 2, 3, 4. Now this is like number line. If you look at the left hand side is negative, approaching negative infinity. Right hand side is approaching positive infinity. All right, so the idea now is that if minus 4 is less than x, the best way to understand this is by using x as the subject. If minus 4 is less than x, it means that x is greater than minus 4, right? It means that x is greater than minus 4. Okay, x is greater than minus 4. Okay, mind you, now this question has equal to here. All right, you could have equal to, please take note of that, take that correction. So x is greater than and equal to minus 4. It means that you're looking at values that start from minus 4 and is moving forward. Minus 4 and is moving forward to positive 6. To positive 6, because you say x is also less than and equal to 6, which means that this is a closed boundary because the value must end at 6. So it means that you're looking at minus 4, okay, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5 and 6. That's what set A is, because it's stated. But if they had just said less than 6, x is less than 6, you would have stopped at 5. But you say less than and equal to 6, you have to stop at 6. If it was greater than and equal to 6, it means that it would have been from 6 to infinity. You cannot use sets when you are having infinity. That is why if you look at this now, if you look at this, B cannot work, because okay, in this case now, say x is greater than minus 1. X is greater than minus 1. All right, but it's less than 1. So now in this case now, if it is B, okay, you can use B to not be infinity. In this case now, if it is B, say x is greater than minus 1. Which value is greater than minus 1? Because minus 1 is less than x, so it means that x is greater. Like I told you, use x as a subject so you understand it better. So x is greater than minus 1. It means that the number that is directly greater than minus 1 is 0 and is less than 1. So it means that in this set it's only 0 that is in this set, because it's only 0 that is in between minus 1 and 1. Okay, now but B is not really our interest because we are told to look for A intersect C. So now let us look for C. Let's state set C. Now for set C, they say x is 0 is less than and equal to x. It means that x, like I said, use x as the subject. X will be greater than and equal to 0. If 0 is less, for instance, now if 0 is less than 1, let me just give you an instance. If 0 is less than 1, we all know that 0 is less than 1. It means that 1 is greater than 0. So use x as the subject. So if 0 is less than and equal to x, it means that x, okay, is greater than and equal to 0. So it means that you have to start from 0 and move forward to positive down to 7. So 0, 1, 2, 3, 4, 5, 6, and 7. Why are you stopping at 7? Because 7 is, in this case, x is less than and equal to 7. That's why you must stop at 7. All right. So now A intercepts C now are the values that are common between A and C. That's what intersect means. I've already explained it before. So A intersects C. What are values common between A and C? All right. So if you look at the values that are common between A and C, 0 is there, 1 is there, 2 is also there, 3 is there, 4 is there, 5 is there, and 6 is there. 7 is not there. So this is your answer. All right. All right. So we'll be looking at another crucial aspect of this code, which is called logic. Now, under logic, we'll be looking at what we call and statements and let me adjust the camera. Okay, statements and what we call um so statements and propositions. All right, what is a statement? Okay, a statement is a declarative sentence that is either true, which is denoted as T, or false, which is denoted as F, but not both. A statement can neither be can not be both true and false, but it can either be true or false. Okay, for instance, now the statement 2 plus 2 is equal to 4. This is statement now, right? Because we use quotation marks to indicate, all right, or what we call inverted commas. Okay, so it is true. Now another statement, the sun rises in the west. This statement is false because the sun does not rise in the west. Okay, the sun does not rise in the west, so it's false. Now we have what we call logical connectives. All right, so I want you to understand what statements are. Now statements are also called propositions too. All right, so it's not as if they are separate. Now let's look at what we call logical connectives. Now logical connectives, we have the first logical connective, which we call negation. Negation is denoted as like this, P. This means not P. All right, this means not P. So you say, so now basically if P is true, okay, not P is false. So if P is actually true, then not P is false, because this means not P. So if P is true, this is false. Just note that. Then number 2, we have what we call conjunction. Okay, conjunction is denoted as P, then this sign Q. Now what does this mean? This means P and Q. That's what this logical connective mean. All right. Then we also have what we call number 3, what we call disjunction. All right. So disjunction is denoted as P, more like the opposite of conjunction in this sign, P then Q. What this means is P or Q. But the other one is called P and Q. All right, but this one is called P or Q. Now one thing you need to know for conjunction is that conjunctions are only true only if both are true. That is, if both P and Q are true, then that is the only time that they can be true. Now for disjunction they are only true if at least one is true. If at least one, don't worry, very very soon it will become clearer to you as we proceed. All right, so that's for disjunction. So like I said, disjunction is true if at least one is true, while conjunction is true only if both are true. Remember that negation is if P is true, then of course this sign that I told you is false, then this is false. All right, take note of that. Number four is implication. All right, implication is denoted for P and Q. Implication is denoted as P then arrow Q. So what this means is, if P then Q, that's what implication means. If P then Q. Okay, so that's what implication means. If P then Q. All right, so this means that it is false only when P is true and Q is false. The only time it is false is only when P is true and Q is false. That's the only time. So when it is false is when Q is actually false, but at that time P will be true. Now then, what they have what we call biconditional. Biconditional. So biconditional is giving like P, then double arrows like this, then Q. What this means is that P if and only if Q. Now this means that it is true if both have the same truth value. If both have the same truth value, that is the only time that it is true. That's the meaning of that statement. All right, so I will create a summary, okay, of how the truth values combine. Okay, how the truth values combine. So if we have P then Q, PQ. All right, PQ. Now now this is basically for implication. All right, when P is true and Q is true, then the implication is true. Remember what we said about implication, that it is false only when P is true and Q is false. But when Q is true and Q is true, it means that the implication is true. When P is true and Q is false, then the implication is false. Okay, so it is false only when P is true and Q is false. But now, how about when P is false and Q is true? It will be true. Then lastly, if both of them are false, then the implication is true. If both of them are false, then the implication is true. All right. Then now let's look at what we call types of propositions. All right, types of propositions. Okay, so we have three types of propositions. We have what we call tautology, we have contradiction, and we have contingency. Okay. All right. So now, what is tautology? Tautology is always true. That's what tautology means. Tautology in logic. Okay, tautology means always true. Now, contradiction always false. Contingency sometimes true, sometimes false. Tautology, like I said, always true. Contradiction always false. Then contingency sometimes true, sometimes false. It's like in between. Okay, so let's look at the laws of logic. All right, so there are four laws of logic. We have the De Morgan's law, we have the commutative laws, and we have the associative laws, then we have the distributive laws. All right, so now let's start with the De Morgan's law. So the De Morgan's law is given like this. All right, that's for De Morgan's law. Okay, and another one still under De Morgan's law, we have this, more like the inverted form of this. Okay, this is for De Morgan's. Then we have what we call the commutative. Commutative is spelled like this. Commutative, the commutative laws. P Q is Q P, while P the inverted is Q then P. All right, more like if this is this, this is this. Remember, I told you what this sign, this is for disjunction. I told you what this is. This is P disjunct Q, this is P conjunct Q. All right, this is conjunction, why this is disjunction. Don't forget that. All right, then we have the associative. Okay, so when we look at associative laws, we have P, okay, P disjunct Q, disjunct R, then P disjunct Q R. Okay, this is associative. Then distributive is P conjunct Q, disjunct R, then P conjunct Q disjunct P conjunct Q. All right, this is how it